Welcome to energy transition. Energy transition means that we are phasing out fossil fuels, and then at the same time we can get rid of the CO2 emissions that are caused by the burning of the fossil fuels. And this CO2 is ancient CO2 from the atmosphere, and as it now releases back to the atmosphere, we have the challenge that CO2 concentration is increasing. The good news is that we do have a lot of energy on globe. We get more energy from the sun than we need, and we just need technologies to convert and store this energy. These technologies we called renewable energy technologies. As they don't release more CO2 in the atmosphere, then these renewable energy technologies are then sustainable, right? Or are they? At the same time, we hear different stories of, for instance, piles of batteries waste somewhere on globe. We hear problems that old wind turbines blades are being buried underground because there's no way to do recycling it. We hear challenges of critical raw materials being lost. So this was really not supposed to go this way, wasn't it? So what went wrong? We have been very dependent on fossil fuels. We have been dependent on them over 120 years. This is a fossil fuel lock-in that we have. And this goes around everything that we do. It's not just powering the transportation or the electrification of us, but also all in the materials here. Now, when we are turning into renewable energy technologies, we have to be very careful that we are not going from one dependency into another dependency. For renewable energy technologies, in order to get those properties that we want from those technologies, we need critical raw materials. And if we are not able to recover those critical raw materials, we can end up into a material dependency. These critical raw materials don't locate evenly, or are not evenly distributed on globally, and therefore we can have also geopolitical challenges with these things. So how do we end up here? First, I'll introduce you a concept called linear economy. This is something that human beings are extremely good at. So we take something from the ground, we build something from it, and after that we sell this to users. And at the end of life, this material goes to potentially a waste or then in recycling if that's possible. And we make the revenue by selling the products to the customer, and after that, the situation is covered, isn't it? It's actually really similar logic that we have with fossil fuels, because with fossil fuels, we also obtain them from somewhere from the ground, we process them, and then with those we can, for instance, power our mobility, but we also have here a waste stream, the CO2, that is then at the moment increasing the CO2 concentration of the atmosphere. And if we're not careful, what can happen is that the same thing continues with renewable energy technologies. So we are then obtaining the critical raw materials from the ground. We make wind turbines or solar panels. And then if we can't really recycle them or recover the materials, they end up into technology waste. So what can we do? We need to go from linear to circular. In nature, there isn't linear processes. In nature, we only have circular processes. In nature, everything is cyclic and everything is built on that way. We have a water cycle, we have CO2 cycle, we have nitrogen cycle. Nature does not make waste. And therefore, we also have to go into operations that are not creating the additional waste. We have a concept for this. It's called circular economy. And here the idea is that we actually utilize the design phase to design the future technologies so that when they are being produced and used, then after that they can be collected and the materials from these devices can be recovered. However, it's not important that they are just recovered, but we need to recover them in such high quality that they can be reused in new applications. If we cannot reuse them in new applications, we are dependent on the mining of new materials and go back into the material lock-ins. So this, of course, sounds very, very simple. Why won't we do this? What is the challenge there? The challenge here is that the materials that we need for these technologies are not simple. We need very complex materials in order to get those properties that we need in order to power the energy transition. So we need to mix metals on, for instance, on nanoscale together in different kind of alloys and different kind of components. For instance, battery materials, lithium iron phosphate is a good example of this kind of a material where we have on the nanoscale made layered materials. And their division at end of life is not anymore very straightforward. We do also have a lot of recycling processes, so that's not a huge issue. However, we need to have processes that are technologically feasible in order to ensure that these processes are being followed. When we're talking about renewable energy technologies, it's extremely important to think about their recycling strategies in much more detailed already while we are producing these technologies. And there, it's not always very evident that we should go only to elemental recovery of these materials, but we have to think about other alternatives as well. First of all, we can take, for instance, an example of silicon solar panels. The silicon that we use in those is not a critical material. We have a lot of silicon. However, it's very, very pure silicon that we need in solar panels. So we needed to use a lot of energy to purify those materials out. And at the moment, we don't have a very good systems how to recycle these materials back so that we could use that high-grade silicon back into new solar cells. And therefore, it's very important to develop revival systems for energy technologies. This means that we somewhat enhance their lifetime or prolong their lifetime, or possibly a reuse of different components and materials. This is something that we're doing a lot in my research team, and also this is one additional example what we did in collaboration with University of Turku. And in this work, we were looking at the material development for a new solar cell type, dye-sensitized solar cells, which are not yet a lot on market, however, which is in the development stage. And in this graph, we have identified the different material options for different layers of this solar cell type. The colors here indicate kind of how easy or what kind of recovery we have for these materials. So this green color is indicating that these materials are possible to recover with the current recycling processes that we have at economically feasible manner. The red color indicates that we might have technological solutions to recover these materials, but we don't have economically feasible manners to recover these materials. The gray color here indicates that materials that are abundant, so we would necessarily not need to recover them, or that we can potentially even lose them because they are not critical. And then the black color materials here are hazardous materials that we would anyway need to get out. With our analysis, you can see that the state-of-art materials are the ones which have been identified in purple color. So you can see that the state-of-art materials are horrible. We can't recover absolutely anything, and we also have hazardous materials in there. So if we start to having these kind of technologies in large volumes out, we have a big challenge of, can we actually recover these materials, or are they just going to become a technological waste? We have also identified here with the blue a more sustainable design alternative for other materials. So here you can find a path which is recyclable. So all of the critical raw materials from that path are recyclable. However, none of these researchers who were doing this material research knew that this is actually a very good way to enhance recyclability of these materials. So therefore, I have a very good news for you, that we can make renewable energy technologies sustainable.